probabilistic analysis algorithm for UASLOPE software program. Separated into 6 chapters. First is introduction, and after that is a development of UASLOPE. And then I will propose a probability-based reliability design method. And then I will show design examples. And after that is additional work, which is a much more advanced reliability methodology, which is important sampling. And then it's a multiple rows or drill shaft stabilizing slope. And finally, the conclusion part. Introduction. Yes, slope failure usually takes a lot of cost and damage to the highways and the real roads. This is another 2 pictures for slope failures. And usually for the soil improvement, we using the retaining walls, soil nailing, anchor walls, MSE walls, and also we can use drill shaft. So for the drill shaft stabilizing slope, it is relatively inexpensive and it has various techniques. And also it no need to close the road during remediation, and it's also successfully used. So for the design of the drill shaft stabilizing slope, usually the design method have basically separated into 2 parts, method slices and arching theory. For the method slice, without drill shaft, we can take a limited equilibrium method like using the tangential force equilibrium as well as the normal force equilibrium. Then, so we can get the relationship between Pi and Pi minus 1. After we adding the drill shaft, we take another, so the Pi minus 1 after the drill shaft has becoming eta multiplies Pi minus 1. So what is eta? Eta means is a load transfer factor, which means after drill shaft, the interslice force has been reduced from Pi minus 1 into eta multiplies Pi minus 1. So after adding the drill shaft, this equation has becoming the bottom equation, which adding the eta here. So this eta is a load transfer factor. So what is the eta? Eta means which is a ratio between the downslope force over the upslope force. So what is the downslope force? For here we can see that the 3D finite element, this one drill shaft, the upslope force is the area, total area of the stress. And also here is the downslope force, which the eta means is the downslope force over the upslope force, which is a concentrate force ratio. And this is this equation is the latest semi-empirical equation for in 2011 that was generated by John Robert Chi, who has already graduated student with Professor Liang, and he using 41 finite element 3D abacus models to simulate the equation. So basically the equation has 6 parameters. C is cohesion, beta is a slope angle, S is a shaft spacing, D is shaft diameter, phi is a friction angle, and Emerson X is a shaft location. Basically, we can see that this is a comparison between his semi-empirical equation to the finite element result. We can see that clearly that is some kind of bias here for this equation. So the limitations for the deterministic part, basically there are 2 major parts. First one is load transfer factor, that is the eta. It's based on the 41 finite element models, which means some uncertainties and errors associated with the eta function should be accounted for. Second one is soil properties, which means in the latest version of UASLOPE 2.1, the soil properties, for example, C, phi, and gamma, is confirmed. However, due to the nature of the soil boring as well as the engineering judgment, some soils is uncertainty part. So both of these two parts we have to concern about that. So problem statement. First one is usually we take the uncertainties for the soil variabilities are usually addressed by required factor safety. For example, factor safety equals to 1.3 for permanent and temporary slopes without foundations, and 1.5 for slopes for supporting or containing structures. However, the factor safety do not change regardless the variability of soil parameters. And also, nominal factor safety more than 1 is not necessarily safe. And also, more factor safety do not mean the slope is more reliable. And also, in other words, more design and construction cost do not guarantee that it can increase the degree of safety to the slope. Therefore, a development of reliability-based methods should be needed to achieve both safe and economical design. The second one is the development of UASLOPE. For the slope stabilizing geoshaft stabilizing slope, usually we address in two methodologies. First one is increase the resistance to calculate the factor safety, which means resistance here plus the geoshaft resistance over the driving force. And another method is to decrease the stress, which is using arching concept. So the factor safety is equal to resistance over the driving force minus arching effect. And this arching concept has been developed by our group from 2002 and until now. As I mentioned before, the arching theory is related to load transfer factor eta, which means is a force ratio between the downslope force over the upslope force. So in 2002, Liang and Zheng, who simulated a two-dimensional finite element, and also they represent a trapdoor type of arching. This is the trapdoor arching here. So the achievement of Zheng is to develop, first one is develop a limit equilibrium formula using arching concept. Second one is developed UASLOPE 1.0 for ODOT in 2002. However, Zheng's method is using a two-dimensional method to regress the formula. In 2007, Liang and Yaming, who simulated another three-dimensional finite element. And however, the limitations would be, first one is they didn't validate the methodology to present the factor safety of force. Second one is sometimes his load transfer factor is bigger than 1. So in 2010, Elboda he simulated a three-dimensional finite element using Abicus method. And he is using the increase the load and shear strength reduction method, which means he reduced the C and phi until the slope has been failure. And then he got the arching, the load transfer factor equation. The good thing is he got the eta function. However, the limitations is he didn't validate the result of the force. And also, this eta function is very, very complicated because it's related 3 extra eta. So in 2011, Zhang Ruoqi, he simulated another 3-dimensional finite element, and he using a new eta function based on 41 finite element models. And in his equation, the eta function is related with 6 parameters, which is a C, as I mentioned, is C cohesion, beta is the slope angle, spacing, shaft diameter, and this one is the shaft location. And also, Zhang Ruoqi generated another version of UASLOPE 2.1 for ODAT in 2010. The limitations of this slope is, first one is a deterministic method, which couldn't consider the soil variability in real world. Second one is load transfer factor is based on 41 finite element model regression, which means there are some bias inside in the limit in the semi-empirical equations. This is a UASLOPE 2.1, the latest version of the program, and has been used by ODAT and its consultant to design geoshaft and to stabilizing on unstable slopes. This figure is 41. He using 41 finite element models to regress the arching effect, regress the load transfer factor equation. And this is a figure, as I mentioned before. We can see that there are some kind of bias between the his regression and as well as the finite element model results. So the uncertainties and errors associated with the semi-empirical equation need to be systematically accounted for in a probability framework. So third part is a probability-based reliability method. Usually in the deterministic part, we usually choose some kind of factor safety, like factor safety equals to 1.3 or factor safety equals to 1.5. In the reliability part, we have to choose another criteria to guide the design. So what kind of criteria should we choose? This figure has shown us that a reliability index or probability failure, we can choose like 3.0 as the performance level is above average, or we can choose 2.5 is below average. And if the reliability index equals to 2, which means the performance level is poor, it's not suggested to use. And this table is from the sources based on the Corps of Engineers in 1997. And in our design, in this presentation, we're using the reliability index equal to 3 to guide the design, which means that when the reliability index equal to 3, the corresponding probability of failure is equal to 0.00135, which means it's 0.1%. So the flowchart of the Monte-Carlo method for geoshaft flow system would be, first one is collecting data. Second, we choose the target reliability index equal to 3. And then we select different shaft location as well as different spacing and diameter. And then we calculate the factor safety based on limit equilibrium method and arching theory. And after that, we make a Monte-Carlo calculating for the total sample numbers, which is a random numbers. And finally, we get the reliability index beta. And if the reliability index data is less than the target, we have to choose different shaft location and the different spacing and diameter again to optimize the design parameters until it satisfies the target. And then we get the design result. So how do we realize the flowchart in a program? First one, we import the slope and geoshaft geometry in C++. And second one, we read in 3 data files, which is a cohesion, friction angle, and unit weight. All of them are following log normal distribution. And also, as I mentioned, the load transfer factor is also uncertainty. So we read in the bias or eta, which is also following log normal distribution. And after that, we calculate the fact safety once. And then we go into back to calculate n times Monte-Carlo simulation. And finally, we get one value of the reliability index or probability failure. So for the failure mode in the geoshaft stabilizing slope, fact safety equals to resistance over driving force minus driving arching effect. So the performance function would be fact safety minus 1, which means is this equation. As mentioned before, the load transfer factor is based on 41 points, 41 regressions, which is also a bias here. So how do we consider about the bias? The arching bias is using the ratio between the finite element eta over the computed, which is a semi-empirical eta. And we summarize the 41 ratios and then over the m, which is the mean of the eta of the bias. And also we can using this equation to calculate the variance of the load transfer factor for the bias based on the 41 finite element. So why do we analyze the 41 mean the mean of the bias and the variance of the bias? Because we want to generate a large number of load transfer factors to input into the Monte-Carlo simulation. And we're just using this 41 as a base to generate a large number of random etas. Also, for the probability density function of the soil parameters, we're using the log normal distribution. And also, the mean and variance we are based on the soil boiling test data. And also, all of them are following IID, which is an independent identical distribution, which means it's no correlation in the soil parameters for every layer and every parameter. This is a methodology how we generate the random variables for each of the parameters. We're using zigzag method. So the zigzag algorithm is an algorithm for Sidu random number sampling, which is based on accept-reject algorithm, and it is the most effective algorithm until now. So for the Monte-Carlo simulation, the big concept is to calculate the indicator function. So how do we calculate the indicator function? We're using the criteria, which is a fact less than, bigger than 1, which means 0, which means we don't need to record the event. And therefore, the probability failure for n times Monte-Carlo simulation would be the extraction of the indicator function, which means we can write down as all of the indicator functions summarized over the total number n. So how do we choose the total number n? We're using this equation. This is the coefficient of variance for the probability failure. For example, is equal to this equation. For example, if we want to choose the coefficient of variance of probability failure equal to 0.3, and the approximate probability failure equal to, for example, 1%. So we can generate the approximately total numbers. And then we go back to simulate the confirmed total number of n. We can perform the Monte-Carlo simulation. And this n is total numbers. So when we introduce the arching theory into the probability failure, which means is fact safety equals to resistance over driving force minus arching theory. And if fact safety minus 1 less than 0, which means we can write down as this equation. And also the corresponding coefficient of variance or probability failure can also write down as standard deviation or probability failure over the mean of the probability failure, which is this equation. Finally, we can get the probability failure value. And how can we calculate the reliability index beta? We can use this equation to transform the probability failure into reliability index. And this function phi is equal to the inverse function of standard normal integral. And also, I want to show you the UASLOPE 3.0 interface. Currently, this interface has just finished recently. So this is the interface of the UASLOPE 3.0. So basically, we changed 3 major parts comparing with UASLOPE 2.1. First one is here. In UASLOPE 2.1, this area is factor safety and also shaft force. So we just change them into probability of failure and reliability index. And also here, we add in another simulation numbers. For example, if you want to generate 10,000 samples, we can input here. Here, the former UASLOPE 2.1 is only one value, but here we adding another value. On the left, we adding a vertical line here. On the left part is the mean of the parameters. On the right part is the standard deviation part. So we can input these two values. This is the cohesion, friction angle, and the unit weight. So all this, for example, this is a 2-layer slope. All of these 6 parameters we can input by ourselves to input the mean as well as the standard deviation for each parameters. And this part is a timing bar, which means how long did you calculate it. So for example, here, using the 2-layer slope, if we simulating 10,000 samples, so it just need 0.4 seconds. It's very fast. And also here, after it finished the calculation, the probability failure the chart has automatically pop out. So you can clearly see that the convergence of the probability failure, or you can just to make a rough analysis for this. But the final value here is showing here. So you can use this final probability failure as the guidance in the design. So here you can see that the probability failure is equal to 0.14, which means it's 14% failure. It's a very big. The probability failure is very big. Corresponding reliability index equal to 1.076. So next, I want to show a design example for this. We're choosing the Ohio 124 slope. And this slope has been analyzed by Leon 2010 in the ODAT report. So I just choosing the same parameter in that report as the same as the project. This is the baseline properties of the example. This only two values we generated. And this part is a deterministic part. If we're using, this is the parameters. If we're using diameter equals to 0.8 meter, spacing is equal to 1.8 meter, and location is in 25.91 meters. The corresponding factor safety equal to 0.9 without gear shaft and 1.277 with gear shaft. So what is the corresponding probability failure for this? Probability failure equals to 96.47% without gear shaft. With gear shaft is 2.8%. However, in the design guide, if we want to satisfy the reliability index equal to 3, which means probability failure is approximately equal to 0.1%, which means 2.8% is not acceptable. We have to change different locations as well as different spacing and shaft diameters to put as an input to redesign game. And this is a final design result for all of them, with diameter equals to 0.6 meters to 2.4 meters, which is approximately 0.6 meters is approximately equals to 2 feet, and 2.4 meters is approximately to 8 feet. Spacing for the diameter over diameter equals to 1, 2, and 3 for this. And also the shaft location is choosing the all of the locations in the certified in the ATH-124 slope. So how did we get the reliability index here? Because we just get probability failure from the UASLOPE 3.0. So we're using this equation transformation to transform the probability failure into the reliability index. We can see that if we the target reliability index equal to 3, we can see that this area's design result is satisfy the target. Next one is how do we have to calculate the shaft force. is this trend, go up and going down. And for the design result, how do we perform the final design result? First one, we have to choose the target reliability index, which the design result should satisfy the target reliability index. Second one, we have to choose the shaft force as low as possible, and also the shaft length should be as short as possible. So this is the final design result for using reliability method. And this is a comparison between reliability index and the factor safety. We're just choosing diameter equals to 0.6 meters, which is 2 feet. From here, we can see that reliability index equal to 3.98. All of these two data has the same reliability index, but with different factor safety, which means different safety can achieve the same reliability method. This 4 is also the same, showing the same trend with the same reliability index, but quite different for the factor safeties. And this 3, you can see that this 3 has the same factor safety. However, reliability index is different. So why? Why we get the same factor safety but different reliability index? Because there are 2 points. First one is the arching theory is different because arching theory is based on 41 finite element regression. Using the factor safety is a deterministic part. Eta load transfer factor is confirmed. However, in the practical engineering, the eta is different because he just using 41 regression. Second one is soil properties, because in the practical engineering, soil properties is uncertainty. It's not a confirmed value. So that's why the fact safety is although fact safety is the same, but the reliability index is a little bit different. Okay, next I want to show the additional work for this outside of the student project. First one is a more advanced probabilistic technique in a drill shaft slope system, which is important sampling technique. So usually, if we want to using Monte-Carlo simulation, we have to generate a large number of soil samples to get the probability failure. For example, if probability failure very, very small, which means it needs a large number of soil samples to generate. However, if we move this probability density function approaching to the failure zone, for example here, we don't need to generate a large number of samples, but we can take some soil samples into the failure zone, which means it can dramatically reduce the calculation times. So that's a basic theory for the importance sampling. This is this point is calling the importance point. So the basic function for the importance sampling is this is a Monte-Carlo simulation part. So we can, if we write this equation into the integral, we can write down here, which the fx is the former probability density function for the Monte-Carlo simulation. If we multiply another function calling importance sampling function, and we over importance sampling function, which means it's the same as the former function, and then we can take out as this part as a new indicator function is here, which means we can take out this part as here, so we can generate another smaller, relatively less samples to calculate the fact safety, with which the soil samples is generated from the importance sampling function. And then we can get the probability failure here. So for the calculating the probability failure, how this part we have already known that using Monte-Carlo simulation. So the basic, the most important thing is how we calculate the ratio between fx over the importance function x. So the performance function is here. If fact safety -1 equals to 0, which means we can write down here as this expression of the performance function. And then for the design point of the importance sampling would be mu is equal to this equation. And this is a reliability index beta, which beta is equal to this, is a mu of performance function, mean of the performance function over standard deviation for the performance function. So for the flow chart of the importance sampling technique would be, first one is to specify the geometry slopes, drill shaft and underground water table, and then we obtain the performance parameters for the performance function gx. Then we calculate the design point mu, and after that we generate random numbers based on the new probability density function instead of the former one fx. And after that we the calculation methodology is the same. This part is the same as Monte-Carlo simulation. And also I'm showing the illustrative example is also the HH124. Here is the result. We can see that we calculated 40,000 Monte-Carlo simulation, and this figure is only showing 5,000 samples calculation. This black line is using Monte-Carlo simulation. We can see it's fluctuant. If we're using important sampling, it's converting very, very fast. So for the failure point, we can see that if we're using Monte-Carlo simulation, if we simulate 5,000 Monte-Carlo simulation, the failure point is only like around 50 or 100 here. But using important sampling, the failure point has dramatically increased. And this is a comparison between the important sampling and Monte-Carlo simulation. We can see that here, after the 40,000 Monte-Carlo simulation, the coefficient of variance for the result is very, very small, which means it's very accurate. So after 307 important sampling technique, the result has already get 2.7. After 682 simulation calculations, the probability failure equal to 2.8 to 1, which is very, very accurate. And also here is a comparison between the Monte-Carlo simulation and important sampling simulation for the accuracy. So for the relative error, comparing to the 40,000 Monte-Carlo simulations, the important sampling need only 307 samples to get a relative error to 2.68%. However, if we're using Monte-Carlo simulation, we have to generate 5,000 samples. Also, if we got the relative error with the true value equal to 0.7%, we need 682 important sampling calculations. However, using Monte-Carlo simulation, we have to generate 22,900 to get the same relative error, which means to get the same accuracy. And additional work too for the multiple rows or drill shaft stabilizing slope, which is a Deterministic methodology part here. So why do we using multiple rows or drill shaft? There are two major reasons. First one is target fact safety. The fact safety using one row or drill shaft cannot satisfy the target, no matter how we choose the dimensions of drill shaft, the spacing, and the locations. The other one is the force applied to the drill shaft are excessively very, very large. If we're using one row or drill shaft, then we have to use another multiple rows or drill shaft to separate the load. This figure is a typical cross section divided into slices for slope reinforced with two rows or drill shaft. So in the limit equilibrium method, we calculate the method slice into slice 4 here from the slice 1, slice 2, slice 3, until here is slice I minus 1, until here is slice I. If we're facing another row, it's j minus 1, j, and until the end of the slope n. And also we take out here this figure as the next slice. So the inter-slice force relationship between the PG left and PG right slice, which is writing down as this equation, which is the same as using one row drill shaft, but different eta. Here is eta 2, here is eta 1, because eta 1 is the shaft row number 1. Eta 2 is shaft row number 2. If we're adding another, for example, the number 3, shaft row number 3, which means it's another equation. This one is eta 3, and these two etas is independent. For the optimization strategy, for example, first one, the global factor safety should be equal or bigger than target. For example, we can choose 1.5 here. And also the lateral deflection of the drill shaft should not exceed the prescribed service limit. Say, we can choose in ½ inch here. However, in ODAT, we usually choose in 2 inch for here. Third one is the location, and the drill shaft should depend on site accessibility and the local availability for the construction equipment. And furthermore, optimization strategy to minimize the cost of reinforcement, the net force or drill shaft should be as low as possible, and also to minimize the total cost of concrete. The total volume of drill shaft should be as small as possible. Okay, the illustrative example here, and this example is artificial slope. And this is parameters here. This is a 6 layers slope. This is a result using one row of drill shaft to calculate the design result. We can see that no matter how we choose the diameters or the parameters or spacing or diameters from 0.6 meters to 2.4 meters, we couldn't get the target factor safety 1.5 here. And also the shaft force is extremely very high. It's like around 500 kilonewton, which is it's like 100 kips. So we design using 2 rows of drill shaft. We can see that the factor safety here is satisfy the target. However, some force here is also extremely very high. It's like 322 kilonewton, which is almost 60 kips here. For the drill diameter equals to 0.6 meters. Then we perform another row of drill shaft, which is 3 rows of drill shaft. And we can see that we output the factor safety bigger than 1.5, and also we output the shaft force on this is less than 200 kilonewton. So we got this final 2 design result. And then we analyze the deflection service limit for the drill shaft here. Deflection is for each row of this is less than ½ inch, which is 12.5 millimeter. This is 11 millimeter. So we can calculate all of these 2 combinations of the drill shaft volume. So we can see that the total volume over here, combination number 2 need less volume of drill shaft. So we tentatively choose combination 2 as a design result for the multiple rows of drill shaft here. Okay, for the conclusions, first one is UASLOPE 3.0. So the reliability-based methodologies has been developed, and also the UASLOPE 3.0 shows that the spacing, the location, diameter, and length of drill shaft are the fundamental design parameters. And also the model error of the semi-empirical load transfer prediction equation can affect the computed probability failure. And also for the import sampling part, import sampling is suitable to employ it into the drill shaft stabilizing slope, and also it's very efficient and it's very quickly calculation if we're using important sampling. However, we have to choose the accurate and appropriate important sampling function. Conclusion 3 is multiple rules. Multiple rules can affect the or the global fact safety for a large field slope and can reduce the net force. So basically, why do we using multiple rules? We want to increase the fact safety. We also want to decrease the shaft force for each road or drill shaft. So until now, the Ohio student project has all of these tasks has done. As a recommendation for the implementation, first one is in our illustrative example, ATH 124 slope, the mean and variance of cohesion, friction angle, and unit weight is just choosing as a KK's forms papers from in 1999, and in the futures design, we have to calculate it based on the measurement of field test. Second one is in the UASLOPE 3.0 program, the model errors, also the soil parameters are using log normal distribution. We didn't include other distributions. So maybe other distributions will be included into the next generation of UASLOPE program. First one is extended the research grading coding of UASLOPE 2.2 and UASLOPE 3.0 into a user-friendly program as well as user manuals. And also we have to develop, second one is develop a more accurate semi-empirical equation for the load transfer factor. So why we have to develop a more accurate? Because the load transfer factor until now is some kind of bias, and also the cohesion, if cohesion equal to 0, which means the eta equal to 0, we have to eliminate that part. The third one is analyzing a different combination for the load transfer factor based on different configurations of drill shaft, such as staggered arrangement or arched shape. So why do we analyze this part? Because sometimes we're using one straight row or drill shaft, which means it couldn't get the target fact safety or excessively very large shaft force. And we're using multiple rows of drill shaft can eliminate this part. However, if we choosing, for example, a staggered part of the drill shaft, maybe this is much more effective, and it's much minimize the construction cost, instead of using multiple rows of drill shaft or the drill shaft and anchors or combination or something. So we have to analyze this part because this is very important and for the practical engineering. And number 4 is develop a more efficient algorithm to calculating multiple rows of drill shafts, because currently we're calculating this artificial slopes, the 6 layers. I just showed that if we're using 3 drill shafts, we have to calculate like 6 hours or 7 hours to get the final design result, because it's a millions combination for the 3 rows of drill shaft, different locations, different shaft spacing, and different shaft diameter. So it's a millions. It's especially the location is very, very large, which means we have to choose a large number of combinations. So future, we have to develop a more efficient and more quickly method to calculate multiple rows of drill shaft. And number 5 is extend the method for multiple roads and drill shaft stabilizing slope on the static loading condition into seismic condition. And also we published some journal papers which is related on this project. And this is some journal papers for that. And thank you. All right.
Okay, we're now going to open the presentation up to questions. Those of you in the room may voice your question. Please speak loudly. If you're on the webinar, you can either type your question into the chat pod on the lower left-hand side or unmute your phone by pressing *6.
Force output. Where are you deriving that?
Oh yeah, Alex's question is why do we remove the shaft force in the UASLOPE 3.0? I just output the shaft force in the TXT file, so you just locate in the text file. Yes.
Okay, well, if there are no more questions, we're going to go ahead and conclude the presentation at this time. This presentation was recorded. It will be available on the research website if you want to go back and look at it later. You'll also be able to download a PDF of the PowerPoint presentation as well as the final report. It'll be up on our website in a couple of weeks. You can get that from www.dot.state.oh.us/research. If you have any other questions you'd like to forward on to the research team, you can email those to research@dot.state.oh.us, and we will forward them on to them for your responses. If you are listening from an ODOT district, please make sure you send your sign-in sheet to Victoria Bill in the Ohio LTAP Center. Otherwise, we thank everyone for participating and hope you have a good evening.
Thanks.